In my mind, there's three basic systems with water. We've got chill water, condenser water, and hot water. Chill water is basically your big air handlers with a valve on it that have water coming to them, are chilled water. You drop in your water temperature 45, 50 degrees, whatever it may be, and then you're passing air over that coil to remove heat from the air.
And then we've got to maintain set parameters on that water in order to achieve processing parameters, you know. So just like we run a 45-degree refrigerated coil or a 40-degree refrigerated coil, well, we've got to run a 45-degree chill water coil to achieve the same amount of processing in BTUs between. Specifically, the most important thing is we could do the sensible capacity at 55-degree water and still cool a space where we won't pull the humidity out.
Right.
So we got to get the humidity. To get the humidity, we got to get to 45.
Yeah. So basically what he's saying is, so you have a chill water system. The chillers are maintaining 40, 45, 50 degrees, depending on how they're set up. The reason they do that versus the 55 we shoot for out of an air handler is, like you said, to draw moisture out of the air. So you need that coil to be well below dew point no matter what the dew point is, which pretty much any time 45 is going to be below dew point. So if that coil temperature is nice and low, you're going to wring moisture out of the system. Whereas if you run a 50 or 60 degree water, yeah, you may make 50 or 60 degree air, but you have no way to remove moisture.
And that's something we face. Actually, we have that conversation probably every winter with properties because they want to raise their chill water set points to 55, 60 degrees all winter long. And then they start wondering why everybody is uncomfortable or things just aren't driving right, this and that. Well,
it's one thing to, when they do that, the problem is, like you said, they lose their humidity control. The way to combat that is you raise your discharge temperature on your air handlers, but you do not raise your chill water temperature because you need that coil to stay cold or you won't pull the humidity out. So if the coil's not cold, you're just the humidity's gonna stay in the air. So we always like to just raise up the discharge temperature based on the load of the space and then let the chiller just maintain its temperature all year.
which is better for the chiller. The chiller is going to thank you for that because it doesn't like to run at that 50-something degrees. It'd much rather run at 40-something.
The condenser water would be, like you said, Wayne, like a water source heat pump or the condenser side of a chiller barrel. Typically, it's a cooling tower to the atmosphere that is taking that water, runs a much higher temperature than chill water, usually around 80 degrees, some down to 70, some as high as 95. Just depends on what they're controlling. You're doing your secondary stage of heat removal on that equipment. You're not doing the primary stage of heat removal. So like a chill water system is your primary heat removal source. Condenser water would be your secondary heat removal source. So you've got your evaporator doing your primary, that goes through the condenser, and then we draw temperature out of the condenser to keep the entire circuit cool. So that'd be like a barrel on a chiller, a water source heat pump, self-contained units, which are giant water source heat pumps, basically. Yeah, and then so water circulates through the condenser or around the condenser, draws heat out, it's passed out to the outside of the building via a cooling tower to the atmosphere. And then we have hot water, which you can actually have, and we'll get into this later, but the same piping for all these systems. Well, not all these systems, but you can have a boiler and chill water in the same thing, and you can have a condenser and a boiler in the same thing. Condenser water and boiler in the same thing. So a boiler is just used to heat the water, and then we either have a hot water system for heating, or we have a heater, a boiler, which acts as a heater for a condenser water system, so you don't overcool your condensers and slug compressors by migrating oil. Basically those, we maintain like a 60-degree temperature in the water. The boiler will fire up in the winter. We take out the cooling tower and we circulate water through the boiler to keep that condenser water temp up if there's no load. Whereas with heating, you're actually heating the water up to like 130, 140, depending on how the system's set up, and then you pass that over a coil to warm up the air in the building, or radiant heaters and stuff like that. So
now he mentioned 60 degrees on the system. For a building like Prairie Brooks, that works because they have head pressure control valves regulating water flow on the condensers. There are systems out there that don't have that, and they're just a constant flow,
And you want to run a higher temperature.
you have to make sure those are at a higher temp.
Yeah.
Because otherwise, it's like having a condenser outside at 60 degrees with a 75-degree return indoor. You know, you end up with a similar condition where that you have migration, and it's an inverted temp, right? That can't happen, there's no fan cycle control. So in the Perry Brooks scenario, the valve on the water at each unit is basically working as a fan cycle switch.
All right, so that's our basic 3 types of systems. So what I was saying before with the way you can have a boiler piped in, there's multiple types of systems in each of these systems. So there's 2-pipe, 3-pipe, 4-pipe, common header, but a basic 2-pipe. So a 2-pipe system is probably the most problematic in my opinion, because you have chilled water and hot water running through the same coil on a unit. So say you have a fan coil unit, it has 1 coil in it with 1 valve, and we have a changeover temperature outside. So if it is hotter than say 65 degrees outside, it opens up to a chiller. If it's colder than 65 outside, it opens up to a boiler, and that valve changes operation based on your temperature. So your air handler can heat and it can cool both with the same coil. 2 pipes are very rare nowadays. I mean, you can understand why. I mean, it's just not efficient. It's not a good way to do something. Especially now with the way they load buildings up and stuff. I mean, it's just not good. You end up with, I mean, we see it all the time. The west side of a building gets up hot. You know, it's just, so if you have a 2-pipe system, how do you combat one side being hot, one side being cold? It's really chasing your tail. Our climate here in Austin varies too much. In colder climates where it stays one way or the other for much longer periods of time, it's okay, it's usable, but for here, it's just not feasible. So our temperatures fluctuate too much. We get too much sun load being down south. It just doesn't work. 4-pipe is the most prevalent. So that's 2 pipes for cold water, 2 pipes for hot water. Supply and return for each system. As it states, you've got your chill water comes from the chiller or whatever it is that's doing the cooling. It could be a ground loop or something, who knows. But that goes to your valve, that's 2 pipes, and then you've got 2 more pipes that go to your boiler and then to your heating source. Easiest way for us to control stuff, easiest thing to troubleshoot. You don't have to worry about voting or what one place is doing versus the other place. You can just heat or cool as you need. So that being said, we wanted to talk about in a 4-pipe system. I guess it can actually go in 2-pipe too, huh? Yeah. So in any type of water system, there are multiple ways to pipe them up. So even if you've got a 2-pipe system or a 4-pipe system, you can have common header, dedicated headers, primary pumps, secondary pumps. It just depends on who decided to draw what that day, I guess. There's got to be some method to it.
And you'll see the majority of that back at the main plant.
Yeah.
So the main plant will have, like you're saying, it'll either have a common header system.
So
draw it.
Yeah, I'm about to.
Yeah.
All right. So we'll focus on 4-pipe because that's gonna be. I guess it won't matter because we'll do.
Let's do a chill water 4-pipe.
Yeah. All right. So this is our air handler. All right. So everything has a supply and return, no matter what kind of system it is. 2-pipe, 4-pipe, doesn't matter. Every device has to have a supply and return. It has to have inlet and outlet. One thing that a lot of people struggle with, me included, is supply and return and what the definition is. Because when you come from unit to chiller to cooling tower to condenser water to evaporator, it flip-flops, right? Because to me, supply and return out of a cooling tower is supply is the water going back to the chiller that's been conditioned. Return is the water coming from a chiller that needs to be conditioned. But then you go to the chiller and it can flip-flop. So we always like to refer to things as entering and leaving. It just makes it the easiest. So the entering water on the cooling tower, the entering water on the condenser, whatever it may be, entering and leaving is the easiest way to do stuff for us. So typically we like to just say leaving or entering. building engineers and property managers and stuff, sometimes they get confused. You say supply, what we mean, they might not mean. Somebody may have labeled the thing wrong. You never know. So I like to stick with entering and leaving. So everything has a supply and return. So in theory, this chiller comes out, goes up to the coil, and that's supply water. Then out of the coil, comes back, goes to the chiller. That's a loop. Very simple, 2-pipe cooling, and then you've got your other coil, which would be cooling. This can be heating, and then it would be same thing, down to the boiler. So supply and return out of both of them. So that's a direct feed 4-pipe system. Where things get confusing is when we go to what we call common header or dedicated, and all the different kinds of pump architecture. This is what's referred to as a common header. Both pieces of equipment are sharing the header that goes to the building. So each one can pump into that system at the same time, equally, independently, whatever it may be. They can both pump into there.
And the pump in that scenario is gonna be right there just above where those, yeah, it's gonna be right in that location. We'll
Like
have
that.
one central pump
So-
or multiple pumps
Yeah.
all feeding the same line.
Yeah, so you would have on dedicated, even on ones that have multiple pumps, they're all in typically the header side of it, or not the header, they would be off of the header. From the chiller, or pump pushes, blah, 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 goes to the coil, comes back through, rotates. What we would have is you would have a valve on one of these that could prevent flow through that chiller. That way you can only run one without pushing water through the other chiller. So on a dedicated system, instead of that valve being there, I guess the valve could still be there, you would have a pump for each one, and then that pump is controlled either through the BAS along with that chiller or through the chiller directly. So we just start the chiller and it starts the pump, or we start the pump and it starts the chiller, however it's wired. It can be done many, many ways. As we were saying, this is your basic 4-pipe system. 2 pipes for each piece of equipment, or each process, I should say, heating and cooling. Then we got into dedicated header versus common header. Basically, it's either your pumps can do either chiller, or your pump only does one chiller or the other. So if you have multiple pumps, dedicated would be that pump is only for that chiller. Common is the pumps can do either chiller or both chillers, depending on how the system's set up for flow. So this is a basic dedicated setup. You would have some kind of valve still, or backflow preventer, something to prevent pushing through the other chiller. Whereas in a common would be your pump over here feeding both chillers together. So common comes through the pumps, can push to both chillers. Dedicated is the pump can only push through its chiller. I don't know if there's some kind of financial or efficiency reason. Personally, I like common because we can do lead lag on chillers and pumps. So you have more redundancy for failure. However, there are dedicated systems that have multiple pumps for each chiller, and they can lead lag their own pumps. So you may have 2 pumps, both that can pump through the chiller, and it can flip-flop those pumps instead of like this where I flip-flop through the pumps. or the control system, however you want, or the chillers themselves, whatever it may be.
And I think the cost of install probably plays a factor of that. Because of the common header system, it does require a little more material. There's a lot more programming, there's a lot more that goes into those types of systems versus a dedicated. Dedicated is more simple. 800 Brazos is an example of a dedicated pumps with secondary versus Burleson, which is all common header.
Yeah, I like common header because, as I was saying with the redundancy, if you were to do a dedicated with redundancy with 2 chillers, you now have 4 pumps. Whereas if you do common with redundancy, you only have 2. So there's actually less involved on a common header until you start getting into valves and things like that. But typically nowadays they're putting valves on common and dedicated, so it really doesn't matter.
Are the pumps normally on the inner or leading side of a chiller?
So typically they are on a chiller.
Where does it matter?
It does. If most of them are pushing through a chiller, so it would be on the return side of the building, pushing into the chiller and then out to the building.
Pumping it in.
Yeah. Now there's something we were going to touch on a second, which is called primary secondary. So primary secondary is you have a pump on both sides. You have something that does the primary loop, which is your building, and then the secondary loop, which is like inside your central plant. So that's getting even more into things. So that would be basically a combination of these. So you would have a pump on each chiller that pushes through the chiller itself to a common header, and then you have pumps on the building. And then if you get even crazier, you can get booster pumps. Like if this is a multi-story building, way up here on one of these floors, you could have another pump that helps circulate and keep the pressure even throughout the entire building. Those are fun when you have to find those and they end up in some broom closet in a hallway that nobody remembers is there. Mm-hmm. Yeah. Yep. Yeah, that's actually one of the buildings that I'm talking about. So, oh yeah, I forgot we got that booster pump. But I did a 15-story downtown Houston, and they could not figure out why they were getting no flow up top. Had a new building engineer, hadn't been there for like 6 months. Nobody had been there longer than a year. Nobody knew about it. Pump was down. So, but I mean, they do have their purpose, especially in like real high rises, not our little Austin stuff. You get into like 60, 70-story buildings, and they definitely have a purpose. Although a lot of those stuff, everything's up on the roof. Well, I guess not the chillers, but some of them could be. I don't know.
It depends. I've seen them both ways.
Yeah.
They'll have a large mechanical in the ground level, or it'll be roof.
Yeah. Never been in a big building, so I don't know.
I've heard of them splitting it in the middle before.
I've seen that.
Technically 800 Brazos is that.
In Houston, we did a building that had a large parking garage. And then between the parking garage and the tenant space above it was their mechanical. We'll stick with chill water just because chill water and hot water can all be plumbed the same way. It's really 6 of one, half dozen of the other as far as that. Typically your chill water is always going to be larger than your hot water. If you ever come to a plant and something's not painted and you got both, the bigger one's always going to be chill water. The primary secondaries are good when you have large buildings or a chill water plant that's far away. I'll use Plaza Lake as an example, Plaza on the Lake as an example. The chill water system is in the parking garage, which is probably 150 yards away from the building itself, and the building is 4 stories tall. So you've got a decent amount of head to push through, and all that pipe that runs underground that you have to circulate through. So you can run smaller pumps on your chillers to circulate water through the chiller, and then they feed in, and then the big pump pushes water through the building in order to send it to all the floors. One of the things with primary secondary that is advantageous to it, in my opinion, which is actually not just my opinion, it's a lot of people's, is you're able to set flow through a chiller with your primary pump.
Bypass though.
Well, or a bypass valve. And then that pump can stay at its most efficient rate for that chiller. And then you can vary your building flow with this guy. So if you've got load, but you need to maintain differential pressure across your chiller, you can have basically two systems. You've got your chiller system, which is doing its thing, maintaining its differential pressure across the chiller. And then we've got our building system, which maintains flow and differential pressure, or whatever it's configured to do, through the building itself. These stay constant volume. So they're always running at whatever, let's just say 100%. And then this can actually modulate to go from 0 to 100 to maintain whatever the building is looking for, whether it's set for GPMs through the entire building, or if it's set for pressure control. It can be either way. So one of the things in a chill water system is we have to maintain a certain amount of flow or pressure across stuff for it to work. Like each coil has a pressure rating. So it needs 12 PSI across the coil. So that's, does 12 sound right? I haven't. Okay. So it wants to see a difference in pressure on that. That equates to how much flow is going through it, how much temperature is being changed. So if you've got 45-degree water entering, and then you have pressure loss across the coil, and then you also have temperature loss that reduces pressure as well, or increase, you need to maintain a certain amount of pressure in that system to push water through every coil. So what happens is we end up with a return side of your coil is typically where your valve is, because you always want your supply coming into the bottom of the coil, and then you want your return at the top. That way your coil is always full of water, right?
And you don't cavitate.
Right, and you don't, yeah. So out of the top of the valve, or sorry, on the bottom of the unit, you would have a three-way valve. And what it can do is it can vary the amount of water that goes through that, but whatever doesn't go through the coil returns back into the system. That way we maintain constant flow through the pumps. So that allows us to, in some systems, run a pump at 100% all the time. And then what we would do is we actually have another valve either way up at the top or down in the plant called a bypass valve. And what that valve can do is it can open and close based on that pressure it can be on a constant volume system, or it can be on a variable volume system. So some pumps modulate, some pumps don't. You can have a modulating pump and a bypass valve, or you can have just a bypass valve and no modulating pump. And then what we would do, if this pump's running 100% and it can only run 100%, you would use this valve to maintain pressure across these two lines. That way you got the right amount of pressure going to each coil to maintain what they need. If you have both, typically we modulate the pump first and then the bypass valve. So we would ramp that pump up or down, and then if we still can't maintain that pressure, we would then open or close the bypass valve to help maintain that pressure. That is definitely typical on buildings that don't have a three-way valve on the coil. Some buildings only have two-way valves, and then we have to have a bypass because you have to be able to maintain your flow through the chill water system. So as these open and close, so as these close, this will open. As these open, this will close. So whatever's not getting pushed through the coils goes through this bypass to circulate the system to keep your flow equal. You can have where you have multiple coils and only the top one could have a three-way, and then all your others have two ways. Or you can have three ways on all of them and really make life fun. It just depends on how the system was designed. And then if it's been retrofitted, somebody's changed it later on. But if a pump is constant volume, you're gonna have typically all three-way valves. Or at least your top one will be a three-way valve that's set to a certain amount of flow. And then, like I said, your bypass valve can either be up at the top or it can be down in the plant to help maintain the flow through the chillers. What else on bypass valves?
One of the tricky parts about when we have a three-way or bypass system versus just a two-way with a speed control and pump is the balancing becomes beyond critical. Because if it's not balanced properly, you end up overfeeding water back to the entering side of the chiller, making it too cold. And that chiller is gonna buck you for it. I mean, it's not going to like that, which is gonna cause the whole building to have issues at that point.
Yeah, and you have issues with your chillers too.
Typically, you see those chill water bypass valves on just the variable primary.
Yeah.
On your primary, secondary.
Right.
And most of the time they're at the end of the loop.
Yeah. So, or they're in the plant right off the chillers. So.
I'm just the honorary artist.
Yeah. I have my lovely assistant with us now. She's going to be drawing since my artistic skills are lacking. Holden's going to take over the visual side of this. I didn't bring you up to distract the class. All right, so we touched on common header, dedicated header, primary pump, secondary pump. Are there any questions y'all have about any? So not the second page. The second page we'll get into during the next class. We'll go deeper into like the control function of those items and what they're actually doing and like if you see one, what you should expect out of it. But do you have any questions as far as like how a common header operates versus a dedicated, how 2-pipe versus 4-pipe, primary pump or secondary pump, anything along those lines? No questions? No answers?
Primary's on the moving the water to the children, and
Yeah.
secondary moving the water to the.
Yeah. Yeah. Typically. I mean, I've seen them labeled other ways, but it's, as long as you can know it as primary, secondary, it matters what they call it in the building at that point. So, because the one building I deal with here that has it is actually flip-flop. They call primary the building and secondary the chillers. So, but they just, whoever decided to put the label on it, that's just what they did. Right. So, but,
Anybody could go that.
right? Well, I mean, that goes back to our entering water, leaving water, supply return thing is, I've seen them mislabeled all over the place. I don't know what's what, so just, if you call me and say, hey, my supply water is this, I'm gonna ask you, well, what are we supplying? So, entering and leaving is the best. So if you tell me, hey, my cooling tower entering water is 95 and my cooling tower leaving water is 95, I'll say, all right, well, is the valve open to the spray bar? No, but who knows? One of the things we didn't bring up in all this would be like a heat exchanger. So you can have heat exchangers on cold water or hot water. Also having one steam, which we won't talk about. Heat exchanger is just another coil. So it's just another way to transfer heat or cooling, however you want to look at it. Heat is what they all transfer, but you would pass cold water through it and take it and basically through the plate system draw heat out of another warmer water. You can do it with steam and create hot water by pushing steam through it, and then the lukewarm water becomes hot by sucking heat out of the steam. You can use condenser water to basically isolate a open loop from a chiller. So if you got a chiller you don't want to push an open loop system through, people put heat exchangers on them. That way you can have an open tower with a closed chiller. Holden's gonna, you want to race more?
It's like South Park now.
Yes.
Yes.
Yeah.
South Park F you have to be a little careful with because
Yeah,
they've got the boiler loop there too.
yeah.
Oh, yeah.
So if
Wait, Plaza Lofts has this heat exchanger. Is that
Another one that has, so I don't know if y'all do any work there. 515 Congress is a building downtown. So it uses city chilled water, right? Which is really cold, like right above freezing. It's got glycol in it. It's real cold. You pass that through a heat exchanger, and then there's only a set of pumps in the building that does the building's chill water. So they circulate the building's water over a heat exchanger that's got water coming from the city to cool the loop for the building. So they don't have a chiller. They just have these two heat exchangers. So all we control is the pump speed in that building. We don't do anything else. Nope. They only have two pumps. That's it.
Is that a cheaper option?
It's cheap for them because they don't have to maintain equipment, but they have to buy energy from the city. So Austin Energy sells them based on a BTU rate energy. So however
That's why
many.
they want those Belimo actuators.
Yep. Yeah, to reduce the amount of energy they have to consume. So, yeah, those valves we put in maintain a split, and then that helps us have tighter control of the heat exchangers because there's no process on the heat exchangers. It's just passing water. So their only way to control how much energy they use is at the units themselves. And the tighter control they have of those with those Belimo valves helps them reduce their energy consumption.
So this would be an example of if we had a plated heat exchanger isolating the tower from the equipment.
Yep.
So this would be a closed loop system on a building, and then this tower could be open loop tower. So that we see that at Aspen Lake 1. Aspen Lake 1 has this exact setup actually.
Also the current setup of Los Angeles too.
Yeah.
Yes, yeah.
Yeah. Current? Yeah.
Yeah.
Not permanently, but current.
Oh, that cooling tower they got out there with all that set up?
Yeah, and they've got the big blue thing sitting out there. That's what this is.
Yep, heat exchanger. Yeah, the cool thing about heat exchangers is it lets you have a closed loop system on your expensive equipment and an open loop on your cheaper equipment. And then as long as you keep your heat exchanger serviced, it's less likely that you are going to damage your expensive equipment from chemical problems and things like that because you have a closed loop system that you can easily maintain. So, but you just got to make sure that you clean out your heat exchangers regularly because they get funky fast on an open loop system. So,
Well, that's where chemical treatment becomes abundantly critical
Yeah.
because the tolerances on those compared to a normal like barrel exchanger, night and day. I mean, very slim tolerances versus a barrel, you could dang near have a tube plugged up and still get some kind of heat out of it. Those plateds, I mean, they're not easy to.
differential pressure loss across it, temperature variance. So entering and leaving pressure, if your entering pressure is much higher than your leaving pressure, it's clogged. Just like we check on those, the water source heat pumps, right? So if you have condenser water entering a water source heat pump and it's high, I don't know what your pressures typically run, what would you say?
Say it's 60 pounds entering and on a normal day, 40 pounds, 30 pounds leaving.
Yeah, if it's running 10, well, you've got an extreme pressure loss, so something is plugging that condenser.
that drop on that pressure?
Yeah. So, well, no, so if it's down to 10 PSI, he's saying it runs normally 30, 40. So you have some pressure loss, right? Because you're going from a big open pipe to all these tiny orifices or coils on the condenser. So you're gonna lose some pressure. Just like as we were saying, as I was saying with the valves and maintaining pressure on a coil for cooling, you're always gonna have a pressure loss. You need to, if it's outside of a certain window, that's how you can diagnose a problem. If it's real high, that means you've got something clogging it, preventing flow through it, right? So think of it like a garden hose. You've got however much pressure on this side of the hose, but if you barely crack the valve, it's just gonna peter out, right? Because you've got a metering device, basically. Same thing with like a TXV or an EXV, that's what it does. The tighter it closes, the less pressure that escapes. So that's how you know it's clogged. If your pressures are really equal, then you may have like a bust in one of the lines and it's going through because those things are jacketed a lot, aren't they?
Which ones?
Like condenser coils. Aren't they usually like jacketed and it's got like the spiral coil through it?
Well, it'll be a tube and tube most of the time.
Okay.
On something like that.
Yeah. I was just thinking like what would cause more equal pressures across the two?
Too much flow.
Too much fun?
Yeah, so it's a really high flow, too much volume, which does have its own set of issues. It'll have a very low differential pressure. So the lower the differential, the more flow you have. The higher the differential, the less flow you have, because you have less force behind the water for pushing it through there. The way I would troubleshoot, there's no set one standard like we have on a lot of stuff when it comes to that pressure drop. It is extremely equipment specific.
Yeah.
And so the way I would troubleshoot that is, okay, say I've got a water source heat pump. I've got 85-degree water coming in, and I've got 100-degree water coming out, and I've got 60 pounds of pressure coming in, and say I've got 15 pounds of pressure coming out. That would be an immediate indicator of a flow issue to me, because I have a whole lot of dead differential between the pressures and the temperatures.
Yeah.
If I increase my flow, my expectation is both of those, that differential would decrease.
Yeah, that's one thing to remember is the flow and your pressure are directly equivalent or temperature, not pressure. So the more flow you have through something, the less chance it has to draw heat out. And that's why, like I was saying on coils, you have to maintain a certain differential. So that's where that valve comes into play. So if you have too much flow through a coil, that medium is not in there long enough to draw out heat. So if you've got 55-degree water entering a coil and 55-degree water coming out, you're probably moving too fast through that coil and you're not picking any heat up out of that coil. So the slower something goes across that coil, the more chance it has to draw heat out of it, right? So that's how we can do things with airflow. Like we can reduce airflow across a coil to give the air more time to cool down. So if we need to dehumidify and we have a chill water system, we'll slow down the fan speed and drive that coil all the way open to where it's cooling and slow the air down across it so it has more time on the coil to suck moisture out. And then when we're not dehumidifying, we can ramp it back up. So flow and temperature are always directly related. So too much flow, you won't draw any temperature out. Too little flow, you'll draw. That's why we're saying 80 entering and 100 something coming out. That water spending so much time in that coil, it's gaining a lot of heat. You're not necessarily drawing a lot out of the object, but the water is picking up a bunch of heat because it's sitting in there so long. So.
And then you start playing into the efficiency and wear and tear game, right? So
That's a whole nother subject.
because you're pushing too much water through there, you're not utilizing that water to its best capability and its capacity. And inevitably, your pump is working harder to move more water than it needs to, which then is creating extra wear and tear at the pump level. But the chances are, if you're doing that at each unit, then you factor in, okay, well, my cooling tower, for example, or hell, even my boiler, for that matter, now is trying to work even harder as well because it can't get its differential because all the equipment has too much flow inside. That's probably going to mean your tower itself probably has too much flow, which means it's working extra hard to try to achieve the same amount of deadband, right, that it can't achieve because it's not able to have the water there long enough to process that heat back out of it like it's supposed to. So that end of the system ends up taking a huge punch in the face and just wear and tear, energy cost, everything, that it doesn't need to. On top of that, you know, where normally the building might do fine on one pump, if the system is balanced wrong, it might take 2 pumps on an improperly balanced system to maintain enough flow to even keep flow on some of the upper floors. And so say all the equipment's on the ground floor and you've got 20 stories, well, that if everything's not balanced right and you have too much flow on all the equipment, that water, those pumps may only be able to support flow up to 15 floors. Those top 5 floors may always have nuisance problems nonstop, strictly because they're not balanced well. And there's not enough pump there to overcome that imbalance.
Yeah, it's just like we have that problem with airflow as well. So if you've got an air handler and a bunch of VAV boxes after it, and all your VAV boxes up front are open, they're robbing air from the ones down at the end, or if all the ones at the end are open and all the ones at the beginning are closed, the air will go straight past the ones that are open and go to straight past the ones that are, straight past the ones at the beginning to the ones at the end, because you're not able to build any pressure towards the back of the unit. That's why we always put like our pressure sensors in the middle of the ductwork, or 3/4 of the length down. You don't want them right at the beginning, you don't want them right at the end, because you need to be able to see that entire range. It's the same thing with pressure. That's why a lot of buildings will have multiple pressure differential sensors, one at the top, one in the middle, depending on how the system's configured.
So
That
you
way.
want to see a random fan power box thrown in there somewhere too?
No, that's just poor design. Yeah. The random fan power box placement is, oh, here's a TI, let's just slap this one in right here. So, yeah, that's usually nothing to do with proper design. It's, any TIs are always going to be random. They just need a place to put it, so they put it somewhere. So, and even coming from engineers, it can be that way, because they're working in this much space and they got to fit an extra box to cover the load of that space. So they just find the open spot on the ductwork. So, like Holden said, as long as you maintain the heat exchangers and they get their proper transfers, they're actually really cool. So they just are maintenance intensive, or critical. Let's call them maintenance critical, because they're not really intensive, although they're fun to take apart. We talk about heat exchangers, so like there's ice storage, chillers, right? A chiller can create ice, really, really cold water, and then store it as ice. And then you use your ice as basically a heat exchanger. You pass water over the ice to cool it and make chill water instead of running your chiller all day. So you can run your chiller at night, create ice, and you store ice, and then during the day, you use that as like stored cooling. So it's real popular in like real high energy consumption places where they get dinged for energy during the day. They'll run everything at night, super cool it all, and then during the day they can use the stored energy, so they're not getting charged high kilowatt hours.
Does it just run ice in the chiller?
No, typically there's a storage tank. It's more of like, call it more of an ice slush, slurry kind of mix. It's not like ice cubes.
I haven't seen it here. There are some larger facilities, it builds off of it. It's a less intense version of the ice storage, of where they literally, they just have multiple chillers feeding a whole complex of buildings, that all the chilled water gets pushed into this tank. Right, these big, huge silo-looking tanks is somewhere on the property, and then all the loop pumps for the complex or whatever it is they're using will pull water out of these tanks.
So the domain has that. Austin Energy uses a thermal storage tank.
Yeah,
is what they
thermal-
call it.
That's what they call it, thermal storage.
They have a lot of heat exchangers
Yep.
in there, in the
Yep.
buildings. I was wondering where that fits, because I know there's such a plant somewhere.
Yeah, there is. It's by that. It's over. You know where Diamonds Direct is? It's right over
I
there.
just didn't know how it all.
So it's the same thing. They have a thermal storage tank there, and thermal storage tanks can be done with ice. It can just be really cold water, whatever. You basically cool this giant pool of water, and then you can mix that with the warmer water throughout the day to create a constant, little bit higher temperature. And then they push that through heat exchangers, or like domain 3 and 4 don't have heat exchangers. They use their chill water straight to their equipment. So, but I think 7 and 8 have heat exchangers. A couple of them have heat exchangers. I don't know all those buildings, but like domain 1 has its own system. Domain 2 has its own system. 3 and 4 use Austin Energy's chilled water to do their stuff. They do not have a heat exchanger. I think 7 and 8, maybe like those 2 new big buildings. I don't know. The 2, like 10 and 11 that they just built. We touched those at all?
Not yet.
Okay.
I know 8 has their own chillers.
Okay, 8 does have its own chillers? Okay.
Yeah, I've been in their plant.
But 3 and 4 I know use Austin Energy's chilled water, so.
Okay. Yeah, I think there's a system like that too, like right over the Gover mentioned, right? You've got the pipes going over the streets.
Yeah, the entire Capitol has a chilled water plant, so.
So and if you're on the back side of the Stephen F. Austin building, on the north side of it, you'll actually see all the condenser piping that comes out of the ground on the back side of the building, and then it snakes down the street into a cooling tower plant
Yeah.
that's down off of Sandjack. And so I've actually been to, they've got it's a multi-level mechanical room with chillers and pumps down in that space. I've rebuilt some of the pumps in there. And yeah, they've got a whole deck with about a dozen chillers, all servicing the city.
Yep.
It's just where the city's cooling comes from.
Yeah.
And then they'll have a whole level of pumps, the size of 2 of these tables put together.
Where's that building at?
Right downtown.
Is that by the Bullet Museum?
Yes.
Okay, 'cause I see some big ass.
Yes.
lights out there.
So what they call that's called a district cooling system. So it's a district is what we refer to it in all these buildings. When we say it's district cooling, that means it's coming from like a utilities district, so.
You all know how buildings determine their electrical bill.
It's their highest load.
Their peak load,
yeah.
Right, peak load.
Yep, it's the peak load yeah, so they take and they look at the peak load and that for the year, right? So this is
It's not even for building cycle.
on a yearly, no, it's not building cycle.
Well, that's how HEB was. It was at the building cycle. So like whatever they were charging for.
It's either quarterly or it's by the year on most commercial buildings. It may be something specific for certain ones, I don't know, but anyway, they take that peak load and they use that as their set rate, and then the higher that load, the more they're gonna pay. Doesn't matter if they get it down, and so that's one of their goals is if they have a quarter where the equipment wasn't working properly, they'll have an extremely high peak load amounts. That's why the automation is so extremely critical because, it's like, we'll get into it next class, but staging all the equipment on and things is very important to try to control that. So that, if it doesn't run properly, they have a huge peak load. Now they're stuck having to pay all this extra money that, they probably shouldn't have to pay just because of that one load cycle. That's why it's critical for us to think about those things and think about the efficiency that we're enacting on a system, because we are directly impacting their energy bill. The more efficient we can make it run and the better we can make it stage and operate, the more money we save them in energy costs.